Alright, last video of 8.3. So we're talking about infinite geometric summations, and something that it says right here that it also said on the slide previously was that it doesn't make much sense to calculate the sum of an infinite arithmetic sequence, right? Because if we're just going to keep adding a bigger number to our sum, then aren't we just going to go on till infinity? Or if we keep adding something that keeps getting smaller, then we're going to go to negative infinity. So it doesn't really make much sense to find the sum of an arithmetic sequence. It also doesn't make much sense to find the sum of a geometric sequence that has a common ratio of more than 1. Because when we put that ratio in the exponent, it's going to end up being a bigger number than the previous term. And so if we keep adding these bigger numbers to the sum, then we're just going to end up with a bigger and bigger number. We're never going to end up at a total. We're never going to end up at a sum. So that's why we don't usually find the sums of arithmetic or geometric sequences. However, if a geometric sequence has a ratio of less than 1, then we are able to find a sum. And we can see this from that formula that we just had right here as well. So if we have our initial term times 1 minus the common ratio to the nth over 1 minus the common ratio, if r is less than 1, then what will happen to the r value in the numerator as n becomes larger and larger? So if r is something like, say, 0.5, what's 0.5 to the first? 0.5. What's 0.5 squared? 0.25. What's 0.5 to the third? 0.0625, I think. But either way, it gets smaller and smaller, right? It gets closer and closer to 0. So if this number gets closer and closer to 0, this number right here, so we have our a1, 1 minus r to the n over 1 minus r. So this is our r to the n. If this gets closer and closer to 0, what's really in the numerator? It would just be 1. Because if this gets closer to 0, 1 minus 0 is just 1. So we're left with a 1 up top. And on the bottom, we're left with a 1 minus r. And out front here, we just have this term multiplied by everything in the parentheses. So what we could do is we can simplify this and throw the initial term, a sub 1, we can throw that in the numerator. Because it's just a sub 1 times 1 to get a sub 1 again. So when the absolute value of r is less than 1, the sum of the sequence is the initial term divided by 1 minus r. So in your box here, the sum of an infinite geometric series, write this in for the equation. So that's going to be what we use to find the sum of an infinite geometric series with a common ratio whose absolute value is less than 1. And that's just derived from this formula, which was the same formula that we started with for finding the sum of a finite sum, or the formula for a finite sum. Yeah. So we're using that same thing, and we're just turning it into this because of how the numbers behave. So let's go ahead and find each of these. We'll go the next 2 sums, and we'll let you all try the third one. So for A, we know that our first term is going to be what? Just going to be 0.6. I mean, no, sorry. That's our common ratio. Our common ratio is 0.6. So R is 0.6. Initial value is 4, because if we try to find our zeroth term, 0.06 to the 0 becomes 1, and our initial term is just then 4 times 1, so 4. So we're trying to find the sum, and the absolute value of r is less than 1, so we know that we can use this formula right here. So the sum is going to be 4 over 1 minus 0.6. So 4 divided by 1 minus 0.6. I'll get my calculator out, even though I don't think I'll need it. 1 minus 0.6 is 0.4. We've got 4 divided by 0.4, which is 10. So that means that the sum of this geometric sequence is going to be 10. The sum of this infinite geometric sequence, I should say. So what this is really checking, though, is if we tested this out, we would have the first term would be 4, right? The second term would be 4 times 0.36. So if we have 0.6 squared, so 0.6 times 0.6 is 0.36, and if we multiply that by 4, we end up with 1.44 for our second term. And then our third term would be 0.6 cubed times 4, which is 0.864. And so you'll notice that if we add these terms up, 4 plus 1.44 plus 0.864, and these numbers are going to get smaller and smaller, right? So it's not like this number, when you add them all up, is going to end up at like infinity. It's going to end up closing in on a number. And what we did using this formula was we found out what that number is going to be. So we found out what the number will be once we add up all the terms separately. But we did that all in one step right here and found it to be 10. So let's move that over here now. So now our r is 2/3. Our initial value is 2. And so since absolute value of r is greater than 1 or less than 1, we know that the sum is equal to the initial value over 1 minus r. And so let's use the same formula. Initial value is 2 over 1 minus 2/3. So 2 divided by 1/3 is going to be 6. Yeah, duh. And so similarly to this one, if we found our first value, we would get a 2. Our second value, we would get something less than 2, and third value, something even less than that. And so once we keep adding smaller and smaller values, eventually it's going to get really close to 0, where it's basically negligible. And we're going to end up with a value. Once we add all those terms up, we're going to end up with 6. So like as we get to infinity, the number is going to get closer and closer to 6, the number of the sum. And that's geometric series. I want you all to try this one. It's the same thing. So the sum n equals 0 still, infinity. But you're going to need to find what r is, and we already know what a1 is. So why don't you use that information to try and figure that out. We'll bring these answers to class. We'll clear up any confusion. Make sure you have any questions written down so that we can discuss it in class. And I'll see y'all soon.